of it. This isn't the right one. The bottom is on the top. The opening is on the bottom. No big deal. I just flipped it over. But this is the idea. They said, well, we have some ideas about how bubbles and fluids flow. Let's just try doing this experiment in a different type of glass and see what happens. Now, another consequence of the fact that you don't oftentimes find glasses like this in production means that they didn't actually do this experiment. They let a computer do it for them. Yeah. So, how do you tell a computer to model the flow of bubbles and beer in a glass? It starts with that, which is a mess. But in words, it's really just a fancy version for fluids of Newton's second law. Net force equals mass times acceleration, which is just fancy physics jargon for causes of motion equal descriptions of motion. There are things on the left that are going to act on the bubbles and act on the fluids, and they're going to tell us how we should then expect the bubbles and fluid to move. Now, most of the stuff on the left we're not really going to talk about. This thing with a little g, that's gravity, the fact that the bubbles are on Earth and they experience a force of gravity pulling them down. This one just says that if there's a difference in pressure, there's going to be some force acting on things. This thing on the left is a thing we do not speak of because it's trying to model turbulence, which is really hard. So, sorry, not going there. But this F sub inter is meant to be the interaction forces between the bubbles and the beer. That we're going to talk about, mainly because we can, but also because it's pretty important. Because if you can't just say, computer, here's this equation, go. It's not going to work. You have to say, computer, here's this equation, and more specifically, I think that the bubbles and the beer interact in a certain way. So I'm going to tell you what I think is the way they interact, then I'm going to say go. And you're going to make me a movie, and I'm going to say, yes, that movie looks good, or no, that movie looks bad. So let's talk about what forces might go into this model, into this computer. There are three main forces that are discussed, but we're actually going to toss out two of them, which is great. The first force, drag force. This is basically just friction. Think of it as it's a force that's going to oppose the relative motion between the beer fluid and the bubble as the bubble moves through the beer. You experience drag forces all the time. You go walking outside and the gust of wind hits you. That's effectively a drag force. This thing that's working well. Okay. If you start running fast and then you start feeling a breeze pushing on you. Okay. There's another one that's called an added mass force, which is essentially the force that's needed to move stuff out of your way. So in this picture, there's two different little plates on top of a fluid. You can imagine we take these two plates and we strike them both with a hammer. One of these plates, the small one, will be easier to strike than the other plate with the larger area, because this larger area has to push more of the fluid as that plate is struck. And so there's this, this ends up being called an added mass type thing. If you're trying to accelerate something through a fluid and the density of the fluid starts to matter, then you have to think about the stuff you got to push out of the way as you move through the fluid. And then the next one is a lift force, but it acts in the horizontal direction, which is strange because normally we think about lift forces as causing planes to fly. They push the planes up. These forces come as a result of the fact that along different sides of an object, you'll have velocities of fluid traveling at different speeds. And the side with the faster velocity will have less pressure, so there'll be some net force pushing this thing to the side. So if you're planes, that force acts to push them up. As these bubbles are rising to the top of the fluid, these forces might act to push the bubbles to the side. But it turns out that this force is actually contested and hasn't been experimentally verified. The added mass force we drop out because we think that the bubbles are moving at a constant velocity, a terminal velocity. So we can forget about the fact that they're accelerating, and all we care about in the end is the drag force, which makes this much nicer. So, Now we have this model. We're going to say, okay, computer, here's the deal. Here's the equations we think are right. Here's the force we don't need to include. Now, make a movie. These are snapshots. These aren't the actual movie. We'll go watch the movie. If I can remember where it went. Excellent. Okay, so we're going to step through this a little bit, but to explain what's going on, to make this an easier thing to solve, to tell the computer to do for us, we start with just half the pint glass. We don't need the whole glass, because ideally whatever happens over here on the left is the same what happens on the right. Cool. We're also going to start by assuming that there's no, the bubbles in the gas are uniformly distributed. The same number of bubbles exist everywhere throughout the glass. The concentration is equal everywhere, which is denoted by the color of red throughout the entire glass. Now, as the movie goes on, right, what are bubbles supposed to do? Float, to go up. So we should see the bottom of this glass start to turn blue, which means that there are less bubbles in the bottom. In fact, the darkest blue means 0 bubbles. And then we're interested to see what else happens in this movie. So we'll start. All right, the vertical lines. These vertical lines are meant to represent lines of constant velocity, constant speed, lines of constant speed for the fluid, for the beer as it moves. So, play a little bit. We go on. Okay. So, do we have blue at the bottom?
Yes.
Good. Reality check. What we told the computer to do is by and large doing something it should be doing. The bubbles in total are rising to the top of the glass. What about what's going on the right edge of the glass? Is that red? Oh, what color is it? Green. Yellow, some blues, some colorblind. It's between red and blue. In other words, there is a lower concentration of bubbles on the outer edge of the glass than there is on the inner edge of the glass. Keep that in the back of your head. Going on a little more. Yeah, good. The next thing that's important to start seeing is we're seeing some swirls develop. These circles. Those circles are telling you that the beer is traveling in a circle. Little beer molecules are moving around in the circle along these little rings. Which, if you remember the fact that this isn't your actual glass, the real glass is that thing, and then imagine rotating it around to make a normal glass. This is really telling you that there are donut-shaped vortexes of beer inside of your Guinness glass. Pretty cool. You just can't see it. So, the important part, though, is if these lines mean that the beer molecules are moving in little circles, then if they're going up in the middle, what direction are they going on the edge? Down. The beer fluid is flowing down along the outer edge of the glass. And as it flows down, it's dragging, to colloquially abuse a word, it's pulling the it's pulling the gas bubbles with it. This is what the computer said is what's happening. So, excuse me. Because it's such a pretty thing to watch, I forgot we should watch it all the way through from start to finish.
So what happens in the square glass?
Square. Yeah. That's a good question. He's a thinker. Okay, good. And now by the end, as you would expect and see with the normal Guinness glasses, all the bubbles have now essentially rise to the top, and there once was a head in the top of this glass that's now starting to just bubble off. Cool. Fun, pretty videos. Excellent. So, back to the slides. Okay. So in this slide, there are freeze frames for the pint and the anti-pint who were both run through that same computer simulation. There is no movie for the anti-pint glass, unfortunately, so we'll just sort of talk through the differences. This picture is pretty close to where I stopped and talked us through, but the nice thing in these pictures is they added arrows to those lines of constant speed for the beer molecules, so now we can actually get the direction that the beer is moving. For the pint glass, on the interior, these arrows, believe me or not, they're pointing up, whereas on the outside edge, you can just see a few arrows pointing down. For the anti-pint glass, along the outer edge, those arrows are in fact pointing up. The bubbles are moving up on the outer surface of an anti-pint glass, according to this model. And in the inside, there's a lot of really weird, wonky, funky stuff going on. They're swirling, they're flowing down, they're flowing back up. But the fact that we have 0 bubbles in the bottom means that we still have net flow of bubbles going up. So what we think about bubbles doing is still happening. Okay. So, what happened? That being choo-choo. Choo-choo. I'm empty-handed. Yeah. Actually, great. That was quieter than I thought it was going to be. Okay, so why does this make sense? Now I'm going to try and walk you through the actual reasoning. So far, what we just did was, well, we think this is the force that matters. Here's an equation. Computer go. Here's some videos that look pretty and they seem to be reasonable, but it doesn't make sense. So we're going to have to do this in 2 steps. First, we're going to assume that there is a varying horizontal density. That is, as you look at a constant line, constant height in the glass, you go left to right, the density, in that sense, I mean the concentration of bubbles to beer varies, as we saw in that video. So we'll just start there first. In the next slide, we'll talk about how do we get that varying density. For now, we'll just say, if we have a varying density going from left to right, right to left, can we get circulation? Can we get the motion of bubbles going down on the outer edges and moving up on the inside? So we can think of this in 2 different ways. If we have a varying concentration of bubbles to beer, where in the inside we have more bubbles than on the outside, then those bubbles, all the bubbles, are going to try and rise in the fluid. As they try and rise in the fluid will exert a drag force to try and work against them in the opposite direction they're moving, pointing down. But Newton's third law says, if you push on me, I'm going to push back on you. So if the fluid pushes down on the bubbles are actually also pushing up on the fluid as the bubbles rise. If we have more bubbles in the center, we can think of that as meaning we have a greater drag force of the bubbles on the fluid of beer in the center of the glass. And then the trick to determine if you'll have rotation, if you'll have circulation form. So, all right, well, if I put a stick across here, I have a greater force vector pushing on one end of the stick than on the other, which means that stick is going to start to rotate, which means, we have circulation happening because of a varying concentration of bubbles as you go left to right. Another way to think of this is in terms of relative densities. We could say, well, if there's more bubbles in the center of the glass, then that portion of the glass is going to be, you can think of it as a less dense fluid. You combine the bubbles in the beer into one fancy fluid. Whereas on the side of the glass, if we have less bubbles, it means we have a denser fluid of bubble beer combination. And since denser things sink and less dense things float, then in this scenario we still have the fluid sinking on the outer edges with the fluid rising on the inner edges. And as the beer fluid starts to sink, again, it's going to drag the bubbles with it as it goes. So any questions on that logic of saying, well, if we have this horizontal variation in concentration of bubbles, we can get circulation? We feel good. Great. Now, here's where the shape of the glass finally matters. The shape of the glass is what gives us that varying horizontal concentration of bubbles. The top row are some cartoony pictures of bubbles rising in a fluid, where going left to right, the clock is ticking, forward, sorry. And on the bottom row is an anti-pint glass. That's why the edge of the glass is denoted by these diagonal gray stripes. In each of these little circles, these dots with arrows on the ends of them, those are meant to be bubbles. Now, when we say bubbles are meant to rise, want to rise, it is they're going to rise straight up, not to the left or to the right, but right to the top. In the real pint glass, as these bubbles start to rise and move straight up, as they do that, and if you look left to right, there is now this gap that's been formed between the bubbles and the side of the container, the side of the glass. And when that gap forms, we now have a varying concentration of bubbles as you move left to right. Now we've got denser fluid on the right side of the glass. That fluid starts to sink as the bubbles continue to rise, but as that fluid sinks, it starts to drag with it the bubbles on the outer edge and pull them down to the bottom of the glass, where they go down to the bottom and they do a little circle and they go back up. For the anti-pint glass, as these bubbles start to rise, they collide with the side of the glass container, and you actually now have a greater concentration of bubbles on the right side than on the inside, and now you have bubbles flowing up on the outer edge of the glass, as was shown in that computer simulation. So, all right, how do we do that again? We have two different shaped glasses, the one we always drink out of, the real pint, and this made-up anti-pint glass. The shape of the glass gives us a varying concentration of gas bubbles as you go left to right, and that varying concentration of bubbles is where you get your circulation of flow. Ooh, wow, all right, okay. Now, someone had asked, what about a square-shaped glass, or a glass with vertical sides? Turns out, you can also look at those. Sorry, I'm jumping around. Right, so what about an Erlenmeyer flask? We want to see a demo with an anti-pint glass, right? Why not? We made a movie of that as well. So here's an Erlenmeyer flask, go away, with the Noche Dolce Nitro poured inside. And it's a little tricky to tell, but you can hopefully see a few bubbles in here actually beginning to rise. And then because this Erlenmeyer flask was filthy, they start to do some weird stuff along the surface, start to kind of coalesce and move up in little clusters. But we do, right, the Erlenmeyer flask, the anti-pint glass, the bubbles are rising on the outer edge.
Anyway, right?
Excuse me?
You did drink it, didn't you?
Oh God, no. I was told multiple times, don't drink anything out of this thing. Now, a perfectly vertical glass. You won't get the sinking bubbles. You don't have the widening shape of the glass. You're not going to get the horizontal variation in bubble concentration. You're not going to get the circulation flow. But you can still do a very cool thing with a perfectly vertical glass, which is actually easier to do with a graduated cylinder because it's so much taller. Wrong one. Oh, that's the right one. Where are the movies? Here we go. Go away. If you take a graduated cylinder and pour nitrogenated beer into it, and you tilt it so that one side of it looks like a pint glass and the other side looks like an anti-pint glass, then what we'll have is on one side we have bubbles sinking on the surface, on the other side we have bubbles rising on the surface. So now we have this large circulation pattern within the graduated cylinder tilted to its side. Ironically, this has been known for 100 years. Just not in the case of Guinness. And if you'll indulge me, so the paper, 100 years ago, this was reported in Nature, which if you're not familiar, is like one of the top tier journals in science. The person who found this last name was Boycott, so it became called the boycott effect, and it's something that was used for the sedimentation of blood cells, blood corpuscles, as they like to call them back then. In other words, you want something to sediment, used as a verb, settle. You want the little clusters of grit or blood cells to drop to the bottom of, in this case, a collection of blood. And it turns out that if you just put blood in a vial and tilt it to the side, it'll speed up the sedimentation rate. And he did this, and he wrote up what I think might be the world's most awesome introduction, and so I'm going to read it because it reads like a joke. I have noticed lately. You won't hear that line in the paper these days. I have noticed lately that if oxalated and defibrinated blood is put to stand in narrow tubes, the corpuscles of sediment a good deal faster if the tube is inclined than when it is vertical. Thus, with the tube about 2.7 millimeters internal diameter, there were, after 20 hours, 4, 23, 35, and 42% of clear serum with tubes inclined at 0 degrees, 22.5 degrees, 45 degrees, and 67.5 degrees, respectively. Why he didn't use a graph, I don't know.
Because you'd have to draw by hand.
Yeah. And then he goes on to talk about other versions of the experiment. The last part right now is, what's the future work? What can we do with this knowledge we've now gained? I like to camp. I like to drink coffee. When I go camping and have my coffee, I have a problem in that I have coffee grounds floating around in my mug. Well, I want those coffee grounds to sediment a good deal faster. So fortunately, now I go camping with a graduated cylinder, and I can have the world's best cup of cowboy coffee with this knowledge. So thank you, folks. That's the talk. We're now open for questions. Yes, sir.
Why the darker beers, Guinness?
Ah, good. I'm glad this is an excellent question. Why the darker beers? Well, I've given this talk before. I gave this talk about 5 years ago, and since then, darker beers were the only things I'd seen this in and then consumed. And we have the same questions, and in the paper they say it shouldn't matter on the darkness of the beer. It actually doesn't even have to be a dark beer. It could be an IPA, it could be an ale. What you need is nitrogen. You need an extremely large number of bubbles so that the bubbles act together like a fluid, as opposed to just individual solo bubbles traveling around. CO2, you don't get enough bubbles, so you won't get the circulation from the bubbles, whereas with nitrogen you will. So in the last 5 years, I've consumed a lot of beer. And Tucson is excellent because everyone likes to put things on nitro in Tucson. So I did some of my own research on my own dime and time, and you will watch it happen. It's amazing. You can go to any place that's on nitro. They have IPAs on nitro, you'll see sinking bubbles. You get an ale on nitro, you'll see sinking bubbles. You get Guinnesses on nitro, you'll still see sinking bubbles. My only disclaimer, if you go to a place that's going to serve you an IPA on nitro, they're probably going to put it in a tulip glass, and a tulip glass is an anti-pint glass. It makes it more aromatic, but it kills the sinking bubbles. So there's some caveats there. Okay, but that's a good question. Thank you. Any other questions?
Same effect with sparkling wine?
Will we have the same effect with sparkling wine? And no. And the reason for that is sort of the similar reason as to why it has to be nitrogen. With sparkling wine, we just don't have enough bubbles. And in fact, with sparkling wine, I think there's fewer bubbles than you have in carbonated beer. And so you'll just have, like, the bubbles there's not enough of them for them to start acting like a collection of bubbles as a fluid. They just start acting like individual bubbles going from bottom to top. So no.
You've done this.
With all of them. Yeah. You, sir.
So, can we get a glass rough to the bottom, put a bunch of nucleation sites and try some CO2 beer? Has anyone done this?
Can we take a glass and can we just start scratching the bottom of the glass to make more nucleation sites? Sites where bubbles will form as they outgas from the beer. So a lot of the earlier research was trying to understand the nucleation process. If you can spike up the bubble population, then yeah, it should work. So go for it. Yeah.
So Guinness actually did that. They made a custom pint glass with nucleation cells at the bottom. To increase the amount of bubbles.
Guinness made a special glass with extra
Special edition,
nucleation
I haven't
sites.
known.
Cool. Very cool. Yes.
So is that how hollow stem champagne glasses?
Hollow stem champagne glasses.
Yeah, so if you have a hollow stem champagne glass, it keeps it bubbling for longer. It makes it look like.
I have to confess, I'm not a champagne drinker, so this is a little foreign to me. But
Imagine if the stem didn't end the top
yeah.
went down through.
So probably, if I had to guess, I would say with a hollow stem champagne glass, have more surface area for champagne to glass interaction, which means you have more nucleation sites. So you've got more spots where bubbles can come out of the champagne. But I'd also think that it makes it happen faster. So now it's going to outgas in a shorter amount of time total. I don't know. Yeah, I can argue myself either way.
Maybe you keep champagne cool.
Yeah. Yes, sir.
So, nice beer, quickly escapes.
Yeah, so, okay. You use the word proteins to connect outgas rates between beers with nitrogen in beers versus carbon dioxide. I can't say anything about proteins. So if you have a beer where the bubbles are coming out faster than another beer, we can talk about that. The drag force is a speed-dependent force. So the faster a bubble is moving through a fluid, the greater the drag force is going to experience. So in that case, I would say that might enhance their effect. If you can get bubbles to flow faster through the fluid, then they're going to have a greater drag force. Is a rough guess. Okay? Any other questions? Hand the mic to God.
Our speakers will be So our next talk will be April 13th. Mark your calendars. It will be Pat Kelly, who is going to be down from the University of California at San Diego. And Pat is, if you remember Rachel Livermore's talk from January about the multiply lens supernova, Pat was the guy who was staying up at 4 a.m. in the morning looking at data from Hubble Space Telescope that actually found this thing. So he's not only doing the talk here, he's going to be doing the colloquium in Student Observatory on Thursday because it's a really, really major science result. We hope you'll join us then. It'll be an absolutely cool talk. Again, if you haven't finished our pizza, please do it. There's t-shirts again. And thank you all so much for coming out here. So if you need answer a trivia question, if you did put in for the trivia questions, we do have prizes for you. Please come up to the front and we'll make sure you get something for your efforts.
Date next month?